Hi, my name is Jonathan Wheeler, and I'm a first-year graduate student at Stanford University studying electrical engineering. I'm about to tell you about my research. My research depends heavily on two concepts, superposition and interferometry, and these are not unique to my field. People use these in digital electronics, people use these in communication theory, people use these in pretty much any type of optics that you can look at. They've been used in discovering relativity and LIGO, LiDAR, and a bunch of other really fun stuff. So I'm going to give you a crash course on how this works just now. Now there's two different types of light. There's a light that's generated from an incandescent bulb, and this light is a little bit harder to work with in science because it's what we say is temporally incoherent. It's spatially incoherent, which means quickly saying that the light that's generated from it goes everywhere and it's multiple colors, which makes it kind of hard for science unless you're reading a science book. Now lasers, on the other hand, these are great for science. These are great for science because all the light that comes out of them are the same color, and we call that temporally coherent, and it's spatially coherent, so it goes in the same direction, which makes it great for science, hard for reading, but cats like them, and if cats like them, so should you. So yeah, to review, incandescent bulbs is spaghetti light going everywhere, every color. Laser light, same direction, same color. If you have two laser beams that are in phase with each other, this is referred to as constructive interference, and you have two beams adding up to a really strong signal. If, however, you have your two beams and they're offset so that one beam is going down while the other one's going up, they flatten out, and it's called destructive interference. In my research, we use light that comes out of a laser and we put it into a circulator. That means light that comes in the left side will come out the right side, and light that comes in the right side goes out the bottom side. We then send it through a Y junction, which splits the light in half and sends it around almost a kilometer of fiber, optical fiber, just like used in telecommunications. Finally, it's put into a photodetector where we detect the output. Inside of this kilometer-long loop of fiber, there's a sort of race that happens where light that goes clockwise and light that goes counterclockwise has to travel different amounts of distance. You'll see here that if I rotate the paper, the light that has to go clockwise has to go full rotation and then a bit more. Whereas the light, if it has to go counterclockwise, its finish line actually gets closer and doesn't have to do the full loop. So one light has to go delta L less and one light has to go delta L more. And so before, if they were perfectly in phase, afterwards they're shifted so that they might be out of phase or nearly out of phase. You can tell if it's in phase or not because if it's in phase, it's strong, and if it's out of phase, the signal's almost gone. Using these physics, you can make a rotation sensor. I'm leaving out a lot of the complicated physics so that you can understand the basics, but you can use a rotation sensor like I've described here in an airplane. You can use them in a submarine where it does otherwise have GPS signals. We've also used it in the Mars rover. If you'd like to learn more about this, you can Google online fiber optic gyros and learn more technical definitions of what I'm doing. If you've enjoyed this video, you can check out some of my other content on my website at jamwheeler.com. Thanks for watching.